Picture a uranium fuel pellet the size of a gummy bear. A handful of pellets like it can help power an average home for an entire year. Today, uranium is one of the most tightly controlled materials on Earth, locked behind armed guards and international treaties. But just a few decades ago, people were so casually using compounds of the same element that they were putting them inside their own mouths to make false teeth look more natural.
Will they look like real teeth?
Almost perfectly.
Any side effects?
Mostly later.
Gather enough of uranium's rare fissile isotope, enrich it, and arrange it the right way, and it can erase a metropolis in seconds. How did a dull rock once used to color glass become powerful enough to power cities, destroy them, and leave behind waste that could outlive every civilization we know? The story begins billions of years before the solar system even existed, in the kind of cosmic catastrophe most stars never experience. Ordinary stars spend their lives fusing light elements into heavier ones, but they can never produce something as massive as uranium. To forge an element that heavy, the universe needs something far more violent: the collision of two neutron stars or the explosive death of a massive star. In those brief moments of unimaginable violence, uranium atoms were created and blasted across space along with enormous clouds of stellar debris. Billions of years later, some of that cosmic dust collapsed into the giant cloud of gas and rock that eventually formed our sun, the Earth, and the rest of the solar system. In other words, uranium was part of our planet from the very beginning, locked deep inside the rocks billions of years before the first plants, animals, or humans ever appeared. And it did not just sit there quietly. A meaningful share of the heat rising from deep inside the Earth comes from the slow radioactive decay of a handful of long-lived elements, including uranium, thorium, and radioactive potassium. That invisible heat helps keep the mantle moving, drives plate tectonics, fuels volcanoes, and keeps our planet geologically alive.
Earth, how are you still warm?
4.5 billion years of radioactive decay.
Is that sustainable?
Ask me again in 5 billion years. Don't worry, I'll cook you first.
For most of human history, nobody knew any of this. Uranium was just a heavy, useless rock that occasionally ruined a miner's day. In the silver mines of 16th century Central Europe, workers kept running into a dark, dense mineral that produced no silver at all. They called it pitch blende. Miners associated it with dark, disappointing ore that produced none of the silver they were looking for, and it usually got tossed onto the waste pile without a second thought. That changed in 1789 when German chemist Martin Heinrich Klaproth analyzed a sample of pitchblende and identified a new element inside it. He isolated its oxide, not the pure metal itself, but it was enough to know something new was there. Since astronomers had just discovered a new planet a few years earlier, he named his element after it. For the next century, this newly named element mostly did one job. It made things pretty. Glassmakers added uranium compounds to produce a glass that glows a vivid, almost electric green under ultraviolet light. And it became a genuine fashion trend in the 1800s. It was radioactive enough to interest a modern Geiger counter, but not a miniature reactor sitting beside the roast beef. Nobody thought twice about it because nobody yet knew this rock was doing anything more than looking good on a shelf. That assumption held until 1896 in a lab in Paris. Physicist Henri Becquerel was studying whether uranium salts, after sitting in sunlight, would glow using energy borrowed from the sun. Paris stayed cloudy for days, so he shelved the experiment, wrapping his uranium sample together with an unused photographic plate and sticking both in a dark drawer. When he finally developed that plate anyway, it was fogged with the clear silhouette of the uranium sample, as if it had been sitting in bright light the entire time. It hadn't.
We may have discovered something. Or created a problem. Give it 50 years.
Becquerel ran more tests and confirmed it. The uranium wasn't reflecting or storing sunlight. It was producing energy on its own from somewhere inside the atom. Before this, uranium was a color. After this, it was a mystery. A young Polish scientist named Marie Curie picked up that mystery for her doctoral research, grinding through tons of uranium ore by hand. What she found inside wasn't more uranium. It was two entirely new elements, polonium and radium, both dramatically more radioactive than uranium itself. Radium became the scientific celebrity of the era. Uranium, the element that had started the whole investigation, quietly went back to being the boring relative nobody talked about at dinner. Which made it a little strange that uranium kept turning up at dinner. In 1936, an American dinnerware company launched a wildly popular line of ceramics, and its signature color, a bright orange-red, got that shade from uranium oxide mixed into the glaze. In some of the earliest batches, uranium made up close to 14% of the glaze itself, not the plate as a whole.
Careful with the red plates.
Uh-huh. Are they expensive?
Not yet.
Mm-hmm.
Production of that red glaze stopped in the 1940s, as the government restricted civilian access to uranium and redirected supplies toward the wartime program. Dinner plates weren't the only place uranium ended up. Starting in the 1940s, dental manufacturers began mixing small amounts of uranium compounds into porcelain used for false teeth and crowns because real enamel fluoresces faintly under ultraviolet light and plain porcelain does not. The practice lasted for decades before manufacturers switched to non-radioactive alternatives. None of this seemed especially alarming at the time. Uranium compounds were treated more like useful industrial materials than serious hazards. That changed in a German laboratory in the winter of 1938. Chemists Otto Hahn and Fritz Strassmann bombarded uranium with neutrons expecting to create a heavier element. Instead, their results showed something that looked impossible. Uranium nuclei were producing much lighter elements, as if they'd been broken apart. Physicists Lise Meitner and Otto Frisch worked out what had actually happened. The uranium nucleus wasn't gaining mass, it was splitting. Frisch gave the process a name borrowed from biology: nuclear fission. One neutron splits one uranium-235 nucleus. That split releases energy and more neutrons. If enough of those neutrons reach other nuclei, the reaction stops being an experiment and becomes a chain. For the first time, scientists understood that uranium could release an enormous amount of energy almost all at once. And that realization landed in the middle of a geopolitical nightmare. In August 1939, a letter drafted by physicist Leo Szilard and signed by Albert Einstein reached President Franklin Roosevelt. It warned that Nazi Germany might be trying to build an atomic weapon. The nuclear age had just found its first investor. Soon, the Manhattan Project was born. The problem was no longer finding uranium. It was finding the right uranium.
How hard can uranium enrichment be? $2 billion, 3 secret cities, every genius on the planet.
Natural uranium isn't one thing. About 99.3% of it is uranium-238, which is radioactive but not readily fissile with slow neutrons and cannot sustain the same kind of chain reaction as uranium-235. Uranium-235 makes up only about 0.7% of natural uranium. But under the right conditions, it can sustain a chain reaction. Enrichment means increasing that tiny fraction, and because the two isotopes are chemically identical and differ in mass by only about 1%, separating them is less like mining and more like sorting nearly identical grains of dust by weight. Except you need kilograms of the rare kind. The United States built enormous enrichment facilities in Oak Ridge, Tennessee, consuming staggering amounts of electricity to accumulate a workable quantity of highly enriched uranium. Most of the workers there had no idea what they were building. They just knew not to ask. On August 6, 1945, a bomb built around roughly 64 kilograms of highly enriched uranium devastated Hiroshima within seconds. Only a small fraction of that material actually underwent fission before the explosion scattered the rest, unused. Yet that tiny fraction was enough to devastate a city, kill tens of thousands of people instantly, and prove that the energy hidden inside an atom could reshape human history. 3 days later, another atomic bomb fell on Nagasaki. This one used an entirely different fissile material, plutonium. The Second World War was ending. The nuclear age was just beginning. Almost overnight, uranium stopped being a scientific curiosity. It became one of the most strategically valuable materials on Earth. For uranium, the Cold War was closer to a coronation. The United States and the Soviet Union spent the next 4 decades building enormous nuclear arsenals, testing weapons in deserts, on remote islands, and deep underground.
If we launch back. Then nobody wins. Perfect. Let's call that stability.
It became known as mutually assured destruction. By the height of the Cold War, both sides had accumulated enough nuclear weapons to destroy civilization many times over.
How many times can we destroy the planet? Around 40. Double it, just to be safe.
The bomb had answered one question. Could uranium release enormous amounts of energy? Yes, the next challenge was figuring out how to release that same energy slowly instead. In a weapon, the chain reaction is designed to grow explosively in a fraction of a second. In a reactor, control rods absorb neutrons to keep the reaction steady instead. The heat produced by fission boils water, and the steam spins a turbine. Humanity had unlocked the energy inside the atom. And then, we used it to build an extremely complicated kettle. It sounds ridiculous, but that's exactly what a nuclear power plant really is. Instead of exploding all at once, the reaction is carefully controlled. The heat boils water, the steam spins a turbine, and that turbine generates electricity for millions of homes. Modern nuclear power produces very little greenhouse gas emissions during operation, making uranium one of the most energy-dense, low-carbon energy sources humans have ever used. But controlling the reaction created electricity. It also created a problem that would outlive the civilization using it. In April of 1986, a flawed reactor design combined with a badly executed safety test at the Chernobyl plant in Soviet Ukraine led to explosions and a reactor fire that spread radioactive material across large parts of Europe. 25 years later, an earthquake and tsunami knocked out power and cooling at the Fukushima Daiichi plant in Japan, leading to core meltdowns in 3 reactors. Neither disaster was about uranium refusing to behave. Both were about the human systems built around it failing under pressure. Uranium was controllable. The systems built around it were not always as reliable. There's a stranger problem hiding behind all of this, though, one that has nothing to do with explosions. Splitting uranium leaves behind waste that stays hazardous for an almost unmanageable stretch of time. In Finland, a deep geological repository called Onkalo is being prepared to isolate spent nuclear fuel roughly 400 to 450 meters down in stable bedrock, over timescales extending toward 100,000 years, far longer than recorded human history. Part of the job isn't engineering at all. It's linguistics. How do you warn people not to open something when the warning itself has to outlive every language currently spoken on Earth?
Gloob zorb fleeb glorb zang! Fleeb zang glorb zorb gloop! Oops.
Humans began planning for geological time. Then they discovered nature had already run the experiment. In 1972, French scientists analyzing uranium ore from a mine in Gabon noticed the sample contained less uranium-235 than the natural proportion scientists expected. What they eventually confirmed was that around 2 billion years ago, natural conditions in that same deposit had allowed uranium to sustain a chain reaction on its own. 2 billion years ago, natural uranium contained a higher proportion of uranium-235 than it does today. Groundwater seeping into the ore acted as a neutron moderator, slowing neutrons enough to keep a reaction going. The heat from that reaction boiled the water away, which shut the reaction down until the rock cooled. Water seeped back in and the cycle started again. This pattern repeated for a very long stretch of time, without a control room, a safety officer, or a single human being anywhere nearby. Uranium isn't the rarest element on the periodic table. It isn't even the most radioactive. A random piece of it isn't going to explode in your hand. Its power comes from something much stranger. Very few naturally occurring elements have shaped our world in so many different ways. Uranium helped keep the young Earth warm from within. It made the atomic age possible. Today, it powers millions of homes, and it left humanity with a problem measured not in years or centuries, but in geological time. And here's the strangest part. There are probably tiny traces of uranium inside your body right now. Not because you work at a nuclear power plant or ate anything unusual. Tiny amounts of uranium naturally exist in soil, water, plants, and food. You've spent your entire life on a slightly radioactive planet. Uranium has never decided whether it would become electricity or a weapon. It has never chosen to power a city or erase one. Every one of those decisions was ours. This element existed billions of years before humans understood what power even was. And long after every reactor, every bomb, and every warning sign we've built has disappeared, it will still be here. So tell us in the comments, what surprised you the most? That people once put uranium into dinner plates and dentures? That nature built a working nuclear reactor 2 billion years before we did? Or that tiny traces of uranium may be inside your body right now?